Going live now.
Okay, let's wait a bit.
Yeah, and we're live. Going live now.
Sorry about that. Hi, everybody. Welcome to the session tonight. I am Nancy, co-organizer of PyLadies Amsterdam, and hosting with me tonight is Bhumika, co-organizer of PyLadies Amsterdam as well. PyLadies Amsterdam is on a mission to promote, educate, and advance a diverse Python community through outreach, education, conferences, events, and social gatherings. Tonight, we have a session led by Francesca Manni, who is AI scientist at the Department of AI, Data Science, and Digital Twin at Philips Research. Today, with Francesca, you will learn the basics of PyTorch and how to use it for designing a deep learning model with an outlook on more advanced applications. Francesca, whenever you are ready. You need to unmute yourself, please.
Sorry. Thank you, Nancy, for the introduction. And good evening, everyone. I'm Francesca, as Nancy has already introduced myself, and I'm here to give you a basic understanding about deep learning with PyTorch. And I would like also to thank PyLadies for this invite and the opportunity to learn, because I'm sure that after today I will be teaching I will be teaching to you some basis, but it will be also a learning for me, and that's why I really appreciate and I really like these knowledge sharing sessions. So the topic here is very huge, as you might know and understand. So it's difficult to provide you today all the concepts needed to perform deep learning with PyTorch. But what I would like to give you, it's actually the basis and an introduction on how to use the tool. Because at the end, what I think is that it really depends on the method that you have to learn the tools. So it could be that today you are dealing with PyTorch, another day with another machine learning, deep learning framework, but it's really a matter of how we approach the methodology. And the agenda for today, it will be indeed at the beginning a starting point on deep learning, so a rope up around the deep learning concept. Maybe some of you already knows the basic understanding of deep neural networks. Maybe you are really fresh and new on this topic. So I would like maybe to ask you and to write whenever you want during my talk, my speech, your experience, your approach on deep learning. Maybe you know the concept, you have tried maybe to design a network, or maybe this is really the first time for you to approach with a deep learning framework such as PyTorch. So you can give like a very short introduction about your experience on previous and similar approaches. So yeah, the agenda will go through repeating a bit the concept, the basic concept of deep learning. We will introduce PyTorch, and then I will give you also a very quick outlook on an unconventional learning technique, which is federated learning. Currently, I'm working on this topic at Philips, and I think it's great when you approach like a new method such as AI to see the horizon, to envision what are the challenges right now and how to fix these challenges to make it working in real, so in real practice, which can be very challenging as from my own experience, I know in the medical domain. So there are some fields where we see AI around us and some fields where we still face challenges, and AI needs to challenge itself. So yeah, if we have time, I will give you this intro about the federated learning, and then we go on the hands-on session. So I prepared for you a very basic, I wouldn't say easy, but very straight to the point notebook, PyTorch notebook. And I, as I told you, I want to give you not exercise to find the solution, but really to approach, to know how to approach this tool, which is PyTorch. So about, this is again an introduction regarding the goals of today. Basically, it's more for me. So I would like to start from the basic. I would like you to understand the complexity of the problem, but also I would like to share knowledge with you. So if you know already some tips to share with the rest of the people, please do it. So it's really learning by doing together. And about me, I don't want to go again about myself. I'm a AI scientist at Philips Research. I have a PhD in AI for medical imaging. I have graduated in biomedical engineering, and I am Italian, as you might guess and know. And I have a lot of curiosity. I think this is a feature very important, especially when you approach with the new method, with new concept and topic. Doesn't matter really your background, maybe it can help you, but it's really important to put and to be driven by curiosity. So I think we have this thing in common since you are here today. But let's start with the topic of today, which is deep learning with PyTorch. And as I told you at the beginning, let's wrap up around the concept of deep learning. So you might know that it's a subset of machine learning, and you might know that it's inspired by the human brain. So it uses an algorithm which is inspired by the human brain. And why? Because basically the way how we learn as humans is from experience. So the goal of a deep learning algorithm is to simulate the human-like decision making. And the inspiration, it's done in a way that the way how deep learning models learns is basically to filtering the information as our human brain. So our human brain filters information, and basically by passing a signal through neurons to perform an action. So in this way, artificial neural networks, which are the basis for deep neural net, connect the network together. They filter the information coming from an observation, and at the end, they aim to perform a task, which could be cluster some data, classify some data, or perform a regression task. So basically, the idea behind it's to find some similarity of the data in a very broad level. And the neurons in a deep neural net are divided into different layers. And this is the way also how we learn as humans to process an information. So we have some hierarchy in our brain, and this is also replicated in the neural network. So we have an input layer. We take the input data from the observation. And basically, when we deal with a computer, with a machine, this information is related to numbers, so bits of binary data that the computer can understand. And we need to do some pre-processing, I would say. So you will see in the notebook that we have to perform some processing, some math to standardize the data, normalize the data in a way that we have the data in the same range. This is actually a more neat and clean way to learn the information through our network. Then we have the hidden layer, and in this hidden layer, we perform the computation on the input data. And this computation, actually, it's a non-linear processing unit. So we have a filter, we have some linearity for extracting the feature and for performing some information. And as I told you before, each layer actually takes the output of the previous layer and gives an input. So we have a kind of hierarchy between an hierarchical structure in our network. And the deep learning refers to the fact that in deep neural net, we have more than one hidden layers. So for instance, if you think about an image, like image of our face, we have the first layers that can encode the eyes or the nose by extracting feature from edges, and composes actually the pixel in a way that we can encode a nose or our eyes. And then in the next layer, we might be able to recognize the face. So we have this hierarchical structure in a way that we go from a very simple to a more complex and more abstract representation of our observation. And yeah, I told you that there is a learning process, but how does it go? So it's not like an easy task, I would say. So we need a lot of data, a large amount of information, and we need to iterate through all this data set to compute what we call the cost function. And the cost function is actually measuring, it refers to the difference between the value that we have, the actual value of our observation, and the predicted value. And the lower the cost, the closer we are to the desired output. So we actually need to minimize the cost function to be able to be closer to the output. And yeah, so it's basically an iterative process, what we have in deep neural net, and iterative in a way that we have this going back and forward. And with the going, we perform the forward propagation, the feed forward propagation, where the information is passed. Actually, we expose the network to the training data, and we pass the input through the network in such a way that all the neurons apply their transformation to the information that is received, and it's sent to the next layers. And then we have the back propagation part, which actually it's used to estimate the error, and the error is estimated by the so-called loss function. I will introduce you later. So we need to compare actually and measure how good or bad is our prediction. And we do this by computing the loss and by propagating backwards our information. So we start from the output layer, and then we propagate the loss information to all the neurons that contribute to the output. And when we back propagate, we try to adjust the parameters of our model in a way that our actual value is closer to the output value. So it seems a bit abstract, but we will actually, with PyTorch, we will see that how it goes in practice. So yeah, I want basically to pass this message today that it's not all about coding. So it's very important to understand the problem, to understand our data, to select also the correct deep learning algorithm, and then to really go to train and test, which is another phase where we need to be aware about our model, our parameter, and so on. But let's go a bit into PyTorch. So here I actually left the link regarding the documentation. I guess it's very crucial and very important that you get in contact with PyTorch through the documentation. This is how I learned. Actually, yeah, until 2 years ago, I was using another library, and I approached it by reading the documentation. It's very well done, and you can understand things by trying doing mistakes, by reading the documentation very well. So it's indeed a deep learning framework. It's based in Python, and it has this benefit, which is, I would say, a very great benefit when you work with machine learning solution, which is basically to be accelerated by GPU. So it's based on tensors, and tensors can be run in a GPU level. And we will see later actually what are tensor, what I'm talking about. And yeah, we will discuss it now. So it's the core of PyTorch, and our basically data structure, if you're familiar with the arrays, with the matrices, is basically the same. So basically it's a way to encode the input and the output of your model. It's a way to encode model parameter, very similar to an NumPy array, Python NumPy array, but they can run on GPU. So they can really accelerate the computing phase, which is really, really crucial, especially when we want to perform some computation like the back propagation. This is fully automatized with PyTorch tensors. So we have tensor, which are basically the way how we see data structure in PyTorch. But the first step, if you remember the framework that I've shown you before, the first step for basically approaching to a deep learning problem is identify your data. So we need to load the data, and PyTorch provides two data classes, actually. One, which is the dataset class that actually has stored many dataset with the samples and corresponding labels Actually, today I will only approach the supervised learning task where we have a label. So we want to learn by having our ground truth. What we tell to the model is actually the prediction that we want the model to make. And these data store are actually many. They can be image-based, text-based, audio-based, and in the notebook you will also find the link to see all the data sets that are provided by PyTorch. And sometimes it's very cool to have such a very standalone data set to test your model, to benchmark with an existing data set. And then you have this class, which is a data loader that wrap your data set and make it the data set like an iterable class in a way that we can easily access the data samples, the labels by using the data loader. So you usually load the data. You can do it with a dataset class. You can also do it with designing your own dataset class, and then you pass it in the data loader to be able to iterate through all these samples during the training. So when you want to design here, I give you some tips. We will not do it today. Actually, I'm not really able to share with you data that are personal data or whatever. So I wanted to work with the data set that are already in PyTorch. But if you want to build your data set, you have to basically specify 3 functions within a dataset class. And the first function is init function. So it's actually a function to instantiating the dataset object. So yeah, you say, okay, I want to initialize the directory that contain images and the annotation. And the initialization part is done by this function. Then you have the len function to specify the number of samples, and then the get item function, with whom you can basically create an indexed collection of data. So you load your data and you return in this way, with this function, the sample from the data set at the given index. And this is quite actually great if you want to read an image. So you want to, in this way, you will convert immediately your data into a tensor, and also you will retrieve immediately the corresponding label from that tensor data. So basically, yeah, this is the first step to load your data set. And then it's time to define your neural net, so the core part. And in PyTorch, there is a space, which is torch NN, which provides you all the blocks that you need to use to build your neural net. And every module in PyTorch actually is the NN module, and a neural net is also a module itself, an NN module with many layers, which are actually also kind of modules in PyTorch. And you will as well initialize your module, and then within this module you would define all the operation that needs to be computed in the forward pass, as you see over here. And more specifically, you will see today the linear layer. So it's a module that applies a linear transformation on the input and store the weight and the bias. So yeah, it's here basically the linear transformation with the weight and bias, like the weight, the input data plus the bias. And then we have other type of layers, which is quite important to familiarize with, like the flattened layer. For instance, for the linear layer, we need the contiguous array. We need one-dimensional array. And that's why if we lead with image, we need to convert this 2D into 1D array. And then we need also to apply some nonlinear function. I will not go actually today into all the function, nonlinear function, all the filter, the layer that you might use. This you can indeed check yourself. It's important to know that on top of the linear layer, we need to apply some nonlinearity. And this is the way how we basically learn our task. And at the end, it's all about parameters I told you before. So parameter of this layer, weight and biases that are optimizing with backpropagation. So all these parameters will be stored in the NN module, and they can be also accessed later on. And to actually activate this backpropagation step, we have a built-in engine in PyTorch, which is called Torch Autograd. So if we need, for instance, to optimize the weight and the bias, if we need to perform backpropagation to compute the gradient, because the math behind is basically computing the derivative of the loss function with respect to the weight, and in this way we optimize the weight, and we need to set this required grad equal to true. So this is also quite important, basically also to understand the backpropagation process. So if we want, for instance, to perform only the testing, so we have done the training, we have optimized our parameter, and we want to test our model with unseen data, we have to enable torch no grad. So we don't want to compute these gradients anymore. So those functions actually are quite key in terms of, okay, I compute the backpropagation, I optimize the weight, now it's time to test. And so here I give you an overview of the hyperparameters, which are basically the parameters that might be tuned. And this is also something empirical. Like actually, it really depends on the problem. So that's why I say it is very important to understand your problem. But the very basic hyperparameter are the epochs, so the number of times to iterate over the data set. The batch size, which are the data sample that propagate through the network before we update our parameters, and then the learning rate, so how much we need to update the model parameters. And I mentioned already, like a way to measure how closer we are with our prediction. We use the loss function for that, and it's the loss function that we want to minimize. And actually, to minimize the loss function in a way that we have the best ideal parameters, this is done with an optimization algorithm, and we can choose many optimization algorithms with many hyperparameters. So the problem here is very big. It's actually depending on what we want to focus. And today I told you it's really a matter of giving you the tool, and then when you have the tool, you can play depending on the problem, depending on your network, whether you deal with images, with text, with tabular data, to tune with these so-called hyperparameters. So again, here you see the full training of PyTorch with PyTorch, and you will see also in the notebook, and the basic steps are here in a way that we compute the output based on our model, we compute the loss function, and we optimize, and then we apply the backpropagation. And when this training is done, we will test our train model on unseen data, on test data. So the basic step to start learning are, I repeated many times now, and I have this quote here which is quite meaningful. So we need to start doing to also understand what we're talking about. And this is a bit a timeline, something that I said already. So you will see in the notebook, we will start with downloading the data, and also get some familiarity with the concept of tensor, which is not really complex to me if you already have deal with arrays. And then we will design our network. We'll see some function for preprocessing, and then we go into training and testing. I told you that I want to give you an overview of a technique which is a bit more advanced, and it's very much related on training collaboratively AI models without sharing the data, which is FL, federated learning. But I think it's good that we start the hands-on session. So we start with experiments and exercises, and then if we have left like 10 minutes. In the last 10 minutes, I will introduce you this topic just to give an extra view, and it's very just descriptive. I want to give you the concept and also to gather feedback from you on a reflection on this. So I think I'm done with the presentation itself, and we can go to the notebook. I guess you have access right to the PyLadies GitHub repo. Let me share it with you. I will share to this screen.
I have also put the link in the chat.
Okay.
So then, you can just check that out.
So this is the link. And we have here the notebook with the exercise. Actually, here we have the solution, and I also introduce you the concept of edited learning here, not with exercise, but just to give you an hands-on view also about the topic. So you can open the notebook. Maybe you can leave my presentation open. It's also here in this folder, and you can check some concept. If you have basic question that I have already discussed, you can check it there. I can also repeat, of course. So the goal, as I told you, is to use PyTorch for those tasks that are meant basically for PyTorch, where we see more, let's say, benefit. So it's to design a neural net, train and test a neural net. But basically to give you some time to get familiar with the library, I ask you here to simply create like a tensor using a torch class. I have already imported here the required library, so you can use the torch library to create a tensor, which is a 2x3 matrix with values as 0 and 1. And I ask you to do the same with random data, and there is actually a torch function to do that. I already pasted here. And then just to familiarize with the first operation that are also basic operation done by a neural net, I ask you to concatenate the two tensor along the first dimension, and you can check in the library which function does this. You can use a function, you can do it manually. There are many ways. And then a simple reshaping the tensor to 1 row and 12 columns. So based on the dimension that you will get out of the concatenation, you should be able to perform this reshaping. As I told you, this reshaping is also done within the network. Sometimes it's very much needed if we have one filter of the network with one dimensionality, and we have an input data with a different dimension. So it's something that usually is done also before feeding the network with data. And I will give you some time. You can start practicing, and you can ask me a question about it. Let me see if I can see the chat in the meanwhile. Yeah.
Can you maybe put the PyTorch documentation link in the chat?
Sure. Yeah, so this is the general page, and you can also check the tutorials here. I will also share the more documented page. Yeah, so you see here you have all the functions on the left. In alphabetic order, but for whatever you check for, you can use. Sorry, here it's not really. Yeah, I don't know why I have a limited view. You can use the search query and search for whatever function. It's actually here on the left. I don't know why in this screen it's not really visible. Yeah, sorry, it's also here. I was into another visualization, but yeah. So here, if I want to look for this torch, yeah, so it's very well documented in a way that we have explicitly the function done by the function itself, and all info about the input with some parameters. Here you see the requires grad, so to automatize the backprop process, and then we have also always examples on the bottom part. And yeah, so here there is also a deep understanding of the torch tensor that can have different types, data types. So sometimes it's also a matter of whether we want to compute our operation in the CPU or in the GPU, and we might choose the good type of tensor, also in terms of bit, whether we want a floating point or not, an integer. It really depends on our data, and once we define our data, also our prediction, our model should fit with the same data type. Do we have a question maybe or no? No.
Also, feel free to unmute and ask any questions or drop it in the chat.
Sure. So I will give you a couple of minutes more and maybe present you the solution so we can discuss it together. But I would like at the end of the session today to gather your notebook and see your reflection. Maybe you can also, in a commented way, write down why you did so, why it doesn't work, or why for you it should work better in a different way, and so on. So you can add here maybe some comments, and this is very basic, I know. So when I will present the solution, also you will see it's very basic operations, but maybe later on it would be good to have your notebook and see how you deal with that. Yeah, so let's see together the solution. Yeah, here I ask to create a tensor using the torch class that I have introduced here as a T. You can call it like you want. And so I create in this way the matrix, the 2x3 matrix with values as 0 and 1. So the first row is made by 0 and the second one is made by 1. And this is the way how you structure basically your torch tensor with a square bracket, and depending on the number of column you put a comma. And the second tensor was using random data, and we have this function to generate random data. And you can pass, if you go also through the documentation here, the number of row and columns. So it's also very straightforward. And this concatenation is actually a property of tensor. We can concatenate. Of course, they should have a compatible dimension, but we can concatenate the tensor along different dimension. And here I do it in the first dimension, but we can do it when allowed in a different dimension. And there is also a parameter that can be changed in the cut, the torch cut function. So when I concatenate along the first dimension, I have a matrix, a tensor actually of 4 rows and 3 columns. And the last step was to reshape the tensor to 1 row and 12 columns. I can do that because I have 12 tensor elements, let's say. So at the end, I have one tensor of 1 row and 12 columns. And the function to use, there are many functions that you might think also in Python itself, in NumPy itself. So it's not actually, it's possible to go to a NumPy array. Sometimes I also do the operation in NumPy and then convert to a torch tensor, and there is a function to do that, torch from NumPy. But if you want to do it with the torch tensor, you use this view function directly. So it's also very useful. And yeah, now we go into the practical part. Do you have any questions so far, or maybe you have already deal with tensor before, or arrays or matrices? So it's basically the same the same concept. Oh my god, sorry. Can you hear me?
We can hear you, yes.
Okay, I just see a black screen. I don't know why. Sorry, sometimes it's a matter of my HDMI cable, but yeah, it's going back. Sorry.
No worries.
Yeah. So I say that sometimes it's a matter to know how the libraries explicitly define this object, like arrays and metrics, and how it defines the operation to be applied to these arrays and metrics.
We did lose your screen sharing, but
Yeah.
you're aware? Okay.
Yeah, let me do it again. I don't know really what happens, but I will do it again.
Yes, we can see it now.
Yeah, perfect. Yeah, so the next step, as I told you in the presentation, is to load the data. And here I introduce a function that I would need for the pre-processing step. And with this function actually is part of Torch Vision, which is a function really made for images. So our use case here, I will explain you now in 1 second. It's an image use case. So we will perform a classification task with images, and this torch vision, it's very cool because you can apply many function on images. And with this compose feature of the transforms function, you can combine different function that you apply to the image. So here, for instance, I need to transform to tensor, and I need to normalize my data. And you can define it before, also after, but I create my transformation function to be applying the data set. And as I say here, it's very useful for any data preprocessing or augmentation that we might perform to prepare our data and to augment in a way that we have more data to be fed in the network. So here I leave it a bit open to understand the transform function. Is also a way to get familiar with the Torch Vision library that has several functionalities, like the data set that we might load, and several functions. Very cool for images, I would say. And this is also where I see the added value of PyTorch compared to other libraries when you deal with imaging use cases. So yeah, I would like you to maybe go through this function and understand, and which is the output that you expect out of this operation, out of this function. And continuing, as I told you before, usually we, not usually, I mean, it might be that we train our neural net on a well-known data set, maybe a data set which is present online, which is public, which is not related to any personal data. And it is also done to benchmark with an existing data set, because maybe many people do it. So actually, to prove that your network is working properly, properly, it's very good practice to test it on an existing data set. And this is very simple example. It's based on MNIST, which is a digit classification task. So we have 600 training images of logits and 10,000 test images. And as I told you before, this is already existing in PyTorch. We can take it from there. It's a built-in data set, so we can define the library as I did it at the beginning, and then we can apply the transformation function that I define, and we call the MNIST dataset. And we want actually to perform the training only on the training set, and when testing, we don't want to perform the training. It's quite obvious. And here I actually leave you the link where you can check all the data set. So it's basically it's an image use case. So you will have your data set in Torch Vision. The library is suitable for imaging use cases. And the first one, it's ImageNet. It's also a very big data set with many images, but might include also faces or personal data. And then here you have a lot of data set available. Sometimes, depending on the task, one data set it's indeed more suitable for a classification, a regression, or an object detection task. So in our very simple case, we want MNIST, and as I told you during the presentation part, we need to wrap this data set in a data loader so that we can later on iterate through the class. And here I ask you basically to use this class, so the data loader class, to define explicitly based on this pre-loaded data set, to define your train and test loader. And I mentioned the batch size because it's something that is required within the data loader itself. So this is the first exercise. I would stop here actually, so to understand a bit the pre-processing function, look at the page with all the data set, actually the image based data set. You can also look around and check for other type of data set. As I told you before, you have text data, audio data, and so on. And then how to use this class. And the guideline to learn the class, it's here. So I give you the link with all the functions of the class. And as I told you, I leave you maybe 10 minutes, even less, and feel free to ask questions, also to paste something that you have tried in the chat. Here it's really present and strengthen the part that you create with this class in iterable dataset. It's quite important, and I guess you also have some example on how to create your customized dataset. Should be here. Yes. There is not a real example, but all the functionality to create it are explained here. So the initialization function, the length, and the get item function. But in PyTorch, you also find some example to customize your own dataset. If you have whatever dataset you might have, and you want to create a function for loading the dataset in a specific way. But for now, here you just have to use the predefined dataset, which in your notebook are MNIST train set, MNIST test set, and then creating your data loader. Okay, we have a question like, is it applicable for all deep learning models from dev, right? And what do you mean, dev? What should be applicable for all deep learning models? The transform function maybe, or can you specify your question? Yeah, I assume so. If you ask me whether the dataset data loader is applicable for any deep learning model, it's yes. So it's a PyTorch function. So wherever you build in PyTorch, it enables the loading of data with these two functionality. And transform, yeah, it's indeed a function of Torch vision. So it's not really related to the deep learning net, but to the type of data set. Or if you ask in general, like if the PyTorch is applicable to any type of deep learning network, my answer would be yes. But yeah, you can specify maybe by speaking up or.
Yeah, if you have a question, you can type it on the chat or feel free to unmute yourself.
I don't know. I guess you cannot see me anymore, but I don't know why.
Indeed, we cannot say we can see
Yeah.
the screen.
Maybe you can stop and restart your video.
I'm trying to do it, but it doesn't really change if I click on preview unavailable. Yeah, I don't know. Something happens before, and it's very strange. Yeah, so I try to click, but maybe I stop sharing for a while. Try to. No, doesn't change. Okay. I'm sorry. Actually, I don't know.
It's okay. But okay, it seems you did answer the question from Dev, so
Okay. Yeah. Yeah. So let's go back to the notebook. Yeah, let's see maybe the solution together for this transform function. Maybe if you didn't have time, you can check. You can maybe try to compose different transformations, different function if you want. But for now, we only need those two. I told you it's also it depends on the type of data, and we go to the solution here. So it's very simple. I give you the class. So in a way, you just pass within the class your data set with the batch size, and you enable shuffling the data set. So to create like a more generalizable learning. So this is a way how we create our data loaders that can be iterable and can enable our training loop. And now let's go into the designing part. I also mentioned you the part of the modules. So the neural net, it's a module with several layers that perform the computation inside the module itself. And I start with a very basic, like shallow neural net. You can add how many layers you want. But yeah, this is the solution. I need to go to the previous one. Yeah. So the exercise here is that yeah, I initialize the model with the first linear layer. And as I told you, we have images. Our images are 28 by 28 pixels. So we need to create a contiguous array. And here I do it in this way. So I could do it before with our reshaping function, our view function. Here I decide to do it here. Yeah. And my linear layer would be would have this dimensionality, so the dimensionality of the contiguous array that we give as input, and then I decide to assign to the first linear layer 100 parameters. And I give you as an exercise actually to create the next two layer, keeping in mind, yeah, here actually I have all the text. So keeping in mind that we have in the second layer, which is our hidden layer, we have the output of the previous layer and as input, and then we need to output a tensor of a size of 50. And then we can design our final layer with this information where the output is actually the output of our model. And since our basically output size is 10, we have 10 values to classify in our dataset, which are from 0 to 9. We need to take into account this output size when we design our neural net. And as I told you before, we need to introduce a non-linearity. And I do this with the ReLU activation function. Yeah, also this you can check it and find it in PyTorch to know a bit more. So basically, yeah, this is the model that we want to design, and your task is to design these two layers, so the hidden layer and the output layer. So in our initialization part, we define our layer, and then in the forward, we make the actual computation. And regarding the size of my linear layer, it's a bit what I show you here. So talking about these sides, it really depends actually whether we want a complex model. So the higher the number of parameters in our layers, the higher the complexity. So the amount of nodes, the amount of layer is always adding complexity. Sometimes we want to add complexity, especially when our task is very challenging. Sorry, I didn't get it.
Streaming is on.
Okay,
All right.
and let me also check on YouTube.
I'm also checking.
Yeah, we're good to go.
Nice.
I have a quick question about the complexity. And you mentioned like, yeah, you might want to add more complexity, but then you need more data. Do you have any like rough numbers or sense of how much data you need to add another layer per se? Or
yeah, it's really great as big topic this question. So you ask actually how much data you need when you have a very complex model, complex in a way that we might have, I don't know, 50 layers and 100,000 of parameter. This is really, it's very difficult to give a number. Usually I can define a good data set in size when we have maybe, in the order of 10,000 data samples. And so it's already a good amount of data like this MNIST. And it also depends on the quality of data. So sometimes if we have a very good balancing between the cases that we want to predict, like here the numbers of the logits, or in a binary classification task, like whether the prediction is 0, 1, if it's very balanced, if the data is really good. Actually, with this size, we could really apply a very shallow network, and the network will be able to learn. But if the data set is a bit problematic in a way that is unbalanced and it's noisy, so indeed, as I see here, you can apply some pre-processing step. Normalization is always advised, and actually to understand the function you mean, not to apply, because you have this function also in PyTorch, like torch norm, and as in NumPy, by the way, and I guess also for cropping you have it already. It's not really part of a deep learning library, is also a bit of image preprocessing in this case. So I would also preprocess before and then focus on the deep learning part. But yeah, so it's it really depends, I would say, on the type of data. And
okay.
yeah.
Yeah, that's fair. Thank
And
you.
this is a very shallow network, I would say. So a very complex network would add more layers, but also in terms of parameters. Yeah, I said 100 input in the first layer. So it's kind of in the middle. So usually I start with something very basic, and then you can add and reduce and see how the output might change. But it's always about really looking carefully at your data set, and the lower the amount of data, I would say, the more simple the network, because you might overfit, so let's say, predict well your prediction. And if you have a very simple network, you can a bit adjust it in a way and understand better. So it's a bit closer to be an explainable network, I would say. also here there are, for instance, I remember torch norm. It also explain a bit the normalization, how is it done, and actually normalization also applied to images. It's a bit like centering the image itself. And cropping in PyTorch I have never done, but yeah, there is a function I see here, also part of the transformation function in Torch Vision, which is a center crop, and you can define the size. So yeah, since it's really to accelerate computation on a GPU, and this is what you need for an image use case, PyTorch, it deals very well with this type of transformation. I see a lot of value on that. And maybe I didn't have time to explain you the concept of the ReLU function, this non-linearity. So without this activation function, we just have an affine transformation, like you could see in my presentation, the very basic construction for a neuron filter, which is here. So without the non-linearity, it's just passing the output, the input through an affine transformation, getting an output. Why will the non-linearity, we can give more complexity to the model, and we can learn more complex structures in our data. And I have used ReLU, which is a nonlinear function that assigns 0 to all the values which are minor than 0, and yeah, it's a linear function for the values that are higher than 0. And I paste here now the documentation of PyTorch. It's quite cool that it can draw the function for a very easy understanding. There are many other activation functions, and there is a lot of argument to make which is the best one. Yeah, we have the sigmoid function as well, which is a smoother and more logarithm structure of the ReLU function. Is actually the easier, and there is a lot of hard say because it's kind of a key how you add the nonlinearity, or you add complexity to your model in a way that the model can learn some complex and composite representation of the data. So if we go into the solution, so I ask the output to be in the size of 50, and the input should be the same size of the output, so should be 100, and the same we apply to the final model. So yeah, as I mentioned before, this is not a real deep neural net, but yeah, you can make it deeper with a number of layers, and then the output it's basically the size of our output. So we have 10 values as output within this data set, so we have to put 10 as output size. And here you see I make in the forward pass the real computation to be done. So I reshape the input. This I said many times now, and then I use the layers of the network to really compute the output per each layer, where I add the nonlinearity with the ReLU function. And this is the final model, and this is what I get when I call my network. So going a bit closer to the training process, I mentioned the importance of the loss function. We have many loss functions, so many way to measure how we are far from the output that we want to reach. And here use the cross entropy loss function. It's quite common actually for classification tasks. So we measure the cross entropy between the input and the output. And we need an optimizer algorithm. So we need to decide how we optimize these weights. And we have many optimizer actually. And the difference is also here how we roll out through the optimization process. So we might sometimes go a bit faster with optimization. We might not be so faster because we don't want to skip any updates, model updates. And so Adam is a very popular optimizer. It's a variant of stochastic gradient descent, which is also the basis of the stochastic process, a probabilistic process to perform an optimization. And another parameter is the learning rate. Usually I would choose like around 0.001, but if we choose like a smaller learning rate, it will go faster. Sometimes it will converge, sometimes not. In this case, actually the data set is quite well curated, so our task it will be trained and it will predict very well, so it doesn't really matter. But sometimes it's very important to set the learning rate in a way that is not converging too fast, but converging in a way that our model learns. And then the number of epoch. Also here I set number equal to 10. It's a very easy problem. So after 10 epochs, it will converge and learn, but sometimes we need more. And when we see our loss function that is not converging, we need to add more epochs for sure. And here actually is the training loop. This is also very basic in PyTorch, and I show you in the slide, so you can find it also there. So we have to iterate over the range of epochs, and we have to call the train function to perform the training itself. Where, as I told you, we have the training loader. So now we can really iterate and take the samples, take the labels, apply our backprop. Here, of course, we do some initialization of the gradient. So we set the gradients equal to 0. We compute the output. We need to compute this per each round, the output of our model by calling the model itself and passing the input of the model. And then we compute the loss function. Very bad in this. I guess I have the solution. I know. Yeah, it's here. So I ask you here to compute the loss function. So we have defined the loss function, and it's a very basic computation. So we need to call this function defined here. It's indeed also part of the NN class of PyTorch. You can explore several loss functions, and they're also very well documented. So I ask you here to, based on that class, to give the output of the loss function. And in PyTorch, you will see the input and the output to put inside. Then we do the backprop step, and we optimize the way, take into account indeed the gradients that we have performed and the loss function. And once you will define the loss, if it works, the training will start, and you will see per epoch the metric that you want to visualize. And in this case, I asked to visualize the training loss. There are many metrics that can be performed. Actually, Torch has also a library for not made and yourself the metrics, but there are built-in metrics like the accuracy, AUC curve, and this is a library that you can use as well. I will also post it here. It's Torch metrics. So it's a collection of PyTorch metrics implementation. And let me know if it works. Yeah, so regarding the question I see now regarding the built-in function for accuracy. So there are some collateral libraries like Torch, Matrix, Ignite, I guess, libraries with some built-in function, but in PyTorch you have to define only using PyTorch you have to define your own metrics in terms of accuracy, so the number of corrected prediction with respect to the total prediction, and then you can visualize it during training. Otherwise, you can introduce these libraries that support PyTorch that are very well made for built-in metrics. Yeah. So yeah, time is actually running out. Yeah, the solution also was quite simple, I would say. So once you define your loss, you simply pass the output of your model and the label so that the loss function can measure the difference. Here you can see my training. For instance, here I would also have displayed the metric that I want to track, like the accuracy, area under the curve, and so on. And yeah, I might have waited also for more epochs to converge. It's actually converging very fast. It's a straightforward task, I would say, to compute. And as I told you before, with the Nograd function, I stop computing the gradient and I try to evaluate my model on a test set. Still, I need to iterate over the test set and to measure the accuracy. So in this way, I also manually compute the accuracy as the ratio between the correct prediction and the total number of prediction, and I could achieve a great accuracy, I would say. And yeah, you can use these 3 lines of code to visualize your results, so to see whether the number that you pick as a test, it can be actually also given by the output of your trained model. And this I leave it to you first for a surprise. I also actually put here 2 exercise as optional, so try to change the learning rate, the optimizer, and see how does it change. Actually, here the model is learning already quite well, but maybe you can find some differences and you can yeah, leave some text, just an observation that comes in your mind. And also I give you as an hint to replace this model with a 2D convolutional neural net. So the convolutional neural network, they apply convolutional operations, so they convolve like in a filter function the input to give the output. And in case of images, you can apply 2D convolutional neural net. Is a bit heavier computation, but if you start with yeah, very simple, like I did network, you can do that, and maybe you can find differences also in the learning procedure. And yeah, you can give an insight and how you would proceed. Also, you don't need to write the code. And time, yeah, is almost over, but I would like actually to receive your notebook, in case, I don't know, Nancy, in case they can, you can also send it to me. So my email is it was given in the presentation actually, so you can write me here, and we can further discuss about, yeah, similar topic. I also didn't have time to introduce this topic. Is also in the notebook. So yeah, but
in 3 minutes, Ferry.
yeah, it's a bit yeah, too much. Yeah, I'm sorry for that. Time's actually yeah, flew.
Thank you.
But yeah.
No, it was a very good session. Many thanks.
Yeah, maybe we can discuss about this offline. Yeah.
Sure.
And okay, thanks to you then. Yeah, I will
Thank you,
keep
Francesca.
answering the questions. Yeah.
That joined.
Yeah, I'm very sorry because my camera is not working. I will show you maybe now, but yeah, something happened, and you see, I cannot. So yeah,
I think, yeah, Jitsi is also a work in progress, and it's not the most perfect tool, but
yeah,
because it's free and it's open source, we just choose to use it over a paid
yeah.
tool.
Maybe it's a matter of my laptop as well, but
Yeah.
And it's okay.
Yeah.
The slides were very good, and your explanations also very clear. So thank you a lot.
Thank you.
For
And as I said, yeah, you can use the material, send me some notebooks, some reflection by email, and yeah, we can discuss about federated learning maybe also another time. Or yeah, it was really a pleasure. I also enjoyed. Thank
Sure,
you.
maybe a follow-up session or social federated learning after next year and
Yeah.
everything stabilizes.
Yeah. And I will not miss your session of December. Is the 8th of December, you said, ready or?
And December, I think we have December 21
Okay.
on data drift.
Okay.
All right. Well, thank you, everybody. We are closing the session for tonight. We hope it was useful. Please join us next month and stay in touch through all of our channels. Have a good evening.
Bye.
Bye.